Hello, good morning, everyone. We are starting the computer instruction set today, and I'm starting a few minutes before so that you can join. And before joining, I would like to say something. Number one, I intentionally stopped the chat box with the YouTube live because of some unavoidable circumstances which has occurred in the last class. That is why I have planned to take your questions with the help of WhatsApp messages. Before writing any WhatsApp message, you should write down your section, roll number, and then you write down your message. First of all, I would like to take some questions from you, that whether my screen is properly visible to you and my voice is audible to you, whether you are facing any buffering problem or any other problem or not. So let me repeat this once again. Today we are starting second class of computer instruction set, not second, actually third class of computer instruction set, and I would like to take your questions through the official WhatsApp messages. Before writing any kind of messages through official WhatsApp number, you must write your section name and your roll number. Then you should write it down your message. I would like to take messages from you through WhatsApp, that whether I am properly audible and my screen is properly visible to you or not. So I am waiting for your response. Meanwhile, you can able to send me some messages. So in the previous class, we are discussing in the computer instruction set. So first of all, I am writing, let me give me some time for writing something. So instruction is operand plus operator For example, C is equal to A plus B. This is an instruction where C is the operand location, A is also an operand location, B is also an operand location. For example, A stores 2, B stores 3, so the resultant value will be stored in C is 5, whereas equal to plus semicolon, they are all operators. To represent an instruction, we need an opcode. Opcode is normally represented in hexadecimal number. For example, let us assume the opcode of C is equal to A plus B is FE. Hexadecimal numbers are represented in by H. Hexadecimal number are represented by H. Why we need the opcode? Because computer understands the machine code or binary numbers. Hexadecimal, so C is equal to A plus B semicolon, this is an instruction which cannot be represented in binary number, so we need an representation of this number which can be converted to binary number, so we require FE, which is the opcode of this instruction. Now F can be converted into binary number by 1 1 1 1. E can be converted into binary number by 1 1 1 0. Now this is properly a binary number or binary code or machine code which is clearly understandable. If you have any problem regarding audibility or visibility regarding my lecture, please write it down in my WhatsApp number. Before writing, you must write your name, section, roll number. I repeat, if you are finding any problem, if you have any questions, please write it down in my official WhatsApp number, which is 9434219068, and you, before writing your problem, you must write your name, roll number, section, etc., etc. So I would like to hear it from you whether I am properly audible or not. I am talking about instruction. So first of all, we need some we need to understand what is instruction. Instruction is basically the operand plus operator. For example, C is equal to A plus B. Here C, A, B are different locations where an operand or data may be stored. For example, suppose at A 2 data is stored, at B 3 data is stored. Now we perform now plus, equal to, semicolon, these are operators. By means of plus, value of A and B are added, so 2 plus 3 is added and result is 5, which is stored in C, because equal to operator will store the data or result from right hand side to the left hand side. By semicolon we are stopping this instruction. So this is a high level instruction that I have written. It requires some operands or operand locations. For example, C, A, B, these are operand locations, and it requires some operator. For example, equal to, plus, semicolon, these are all operators. Of any kind of instruction such as C is equal to A plus B semicolon cannot be represented by means of binary numbers. Why we need to represent it by means of binary numbers? Because computer or machine is made of with hardwares or electronic devices such as IC. IC only understand binary codes. So C is equal to A plus B semicolon cannot be represented by binary codes or binary codes. That is why to represent a particular instruction, we need opcode or operational code. For example, C is equal to A plus B semicolon, maybe the opcode is FE. Normally opcode is written in hexadecimal number, that's why I have written H. Now F can easily be transmitted to binary number, that is 1111, and E can easily be transmitted to binary number, that is 0001. Now this is understandable by your hardware or machines. That's why this is a machine code which is understandable by IC. That's why we require the opcode. So an instruction is a combination of operand or operand location plus operators. Example, C is equal to A plus B. Here C, A, B, these are operand location. Here 2, 3, 5, these are operands which are stored in A, B and C respectively. And it also contains some operators. Here in this example, equal to, plus, semicolon, these are basically my operators. Plus is performing addition operation, equal to is performing assignment operation, and semicolon is performing ending of the, denoting ending of the instruction. To represent an instruction, we required an opcode. To represent an instruction in the machine or computer, we required an opcode, and that opcode is represented in hexadecimal number, so that we can represent this opcode by binary, convert this opcode by binary numbers, so that it can be understandable by machine. We need to understand it first. So we are coming back once again. So in computer architecture or organization, we defined as it is defined as a study of components and their interconnection that form a computer system. What are the components of computer? Arithmetic logical unit, register array, control unit. These are different components of a computer, and how they are interconnected, that is also an important point of concern as far as computer organization and architecture is concerned. So to make to run a computer system, we need some instruction, and which is displayed here. C is equal to, this is an instruction. Okay, so a machine or computer supports many instruction. When lots of instruction are collected together, they called instruction set. When lots of instructions are collected together, they called instruction set. And every computer supports certain types of or certain kinds of instruction set. Every computer supports certain kind of instruction set. Now if you have any problem regarding audibility or visibility, please write it down in my official WhatsApp number by writing your section and roll number. Okay, I would like to hear it from you that whether my lecture is audible, properly audible and visible to you. So we know that a computer is basically understand three types of language. Let me write it down for you. So a computer understands high level language. HLL stands for high level language. Example of it is C. Next is it understands assembly level language, or all. Example of it 8085. Then it converted into machine level language. So first of all, we are writing our codes in high level language. For example, C is equal to A plus B semicolon is an instruction written in high level language, which is written in C programming language, which is an example of C programming instruction. Then this instruction is converted into an assembly level programming language. For example, A plus B equal to C. I can write it in this way. Okay, so add is basically the instruction. So to represent this add instruction, we require an opcode. To represent this instruction, we required an opcode or operational code. Let me assume the opcode or operational code for add is FE, which is represented in hexadecimal number. The binary corresponding number of that is this, which is understandable by machine. Okay, next is add C comma A comma B. What does it mean? That means value of A, which is 3. Sorry, value of B, which is 3. Next, value of A, which is 2, are added, and result is, and we perform the addition between A value and B value. So result is 5. This 5 will be stored in C. So this is the high level language. This is the high level language written in C. This is the assembly level language written in some microprocessor supported assembly level language. Now we can convert this assembly level instruction into a machine level instruction or binary code so that it can be understandable by machine. I would like to hear it from you whether I am properly audible or not, and whether my screen is properly visible or not. So in case of the languages, we can define it in this way. So we used to write our program in high level language, then we compile our program. After assembling our program, our all instruction in the program is converted into assembly level language. Then this assembly level language, when we run this program, it converts all the assembly level instruction, will convert itself into binary codes which are nothing but machine level language or understandable by machine level language. Then machine generates the result. So machine will generate the result, say for 5, it generates the result 5. So it generates 5 by means of binary number 0101. Then this 0101 will be converted once again to assembly level language. That means 5. 0101 can be written in assembly level language as 5. 0101 can be written in assembly level language as 5. Then this 5 will be converted into decimal number or high level language, and we display 5. So 5 is my result. Let me take some questions from you. Okay. Okay, so let me explain it once again. Say C is equal to A plus B semicolon. It is basically a instruction written in C, and it is an high level language, a high level language. I repeat, C is equal to A plus B semicolon. It is an instruction written in C, and it is a high level language instruction. First of all, whenever we compile our program, this instruction converts itself into assembly level language. Its instruction will convert itself into assembly level language. Say add C comma A comma B. What does it mean? That means the value of B, which is 3, value of A, which I assume 2, are added together, and result is 5, which is stored in C. Okay, now what happens? To represent any kind of instruction in assembly level language, we need some opcode. For example, add is the instruction presented in this assembly level language. We assume that the opcode of add is FE, which is written in the assembly code. That is why I have written H for that. Now FE can easily be converted into binary numbers, because our machine understands binary binary numbers, this high level language cannot be understandable by machine. It has to be converted into assembly code like add C, A, B. So now it understandable by the machine. Now what happens whenever I execute my program? First of all, the machine code of add, which is FE, converted to binary number. So our machine will understand, or our hardwares will understand, that we are performing the addition operation between C, A and B. Now what is the value of A? Now 2 is converted into binary, B is converted into binary, value stored at B is converted into binary, then we perform the addition. After addition, our result is 5. So we generate our result. Then what happens? Then we are basically reversing it back. That means 5, which is represented in binary, which is nothing but 0101, converted into assembly level language, or that is basically 5. Then assembly level language will convert itself into decimal number to represent it in high level language or user understandable language. Normal user does not understand assembly level codes. So 5 will convert itself into decimal number, because decimal number is understandable by all users. So sorry, this 5 is converted to decimal number. Now this 5 is displayed. That means the result of this instruction is 5. So instruction is a combination of operand and operator, which are operand or operand location, which are operand here 2, 3, 5 are operand respectively, which are stored in operand location A, B, C respectively. So C, A, B, these are operand locations, whereas plus, which is performing addition, equal to, which is performing assignment, and semicolon, which denotes the end of the statement, are known as operators. To represent any instruction, we need a special code, operational code, known as opcode. For example, let me assume the opcode of C is equal to A plus B semicolon, or opcode of this assembly instruction add C, A, B is FE, so that we can easily convert it into binary numbers and we make it understand to the machine. We are about to execute an opcode, about to execute an instruction, assembly language instruction add C, A, B, or a high level language instruction C is equal to A plus B. Okay, so a computer is basically, so this is basically the instruction. What is about instruction? What is instruction set? An instruction set is a collection of instruction. An instruction set is a collection of instruction. An instruction set is a collection of instruction. For example, load B, then we have add A, then we have store T, so load B, that means we are loading the value of B register to A register. Okay, load means we are loading the value of B location to accumulator, or accumulator is basically a register. Accumulator is basically a register which is denoted by ACC. So by load B, what we are doing, value of the memory location B will be transmitted to accumulator. Then add A. What do you mean by that? Then the accumulator value of the accumulator will be added with memory location A and result will be stored in accumulator by default. Why? I shall explain later. Store X. What do you mean by that? That means we are storing the value of accumulator, that means our result, in any memory location, say in a memory location which is known as T. So what we are doing, load B, this is our first instruction, then add A, this is our second instruction, then store T, this is our third instruction. By load B, what we are doing, we are basically loading a value of memory location B to accumulator register, which is denoted by ACC. Then add A. What do you mean by that? Automatically value of the accumulator and value of the memory location A will be added and result will be stored in accumulator register. Then store T. What do you mean by that? That means the value of the accumulator which is generated in the previous case, previous instruction, will be transferred to T location, will be transferred to T memory location. So there are three instructions. There are three instructions presented in this program. In this way, there may be more instructions which are supported by an computer or computer system. The total number of instructions supported by a computer system is known as computer instruction set. I repeat, the total number of, in this example there are three instructions: load B, add A, store T, okay, which basically gives us a simple program for addition with the help of assembly level programming language. There it is possible that not only this three instruction is supported by a computer system, but also more than that instructions are also supported by this computer system. So total number of instruction supported by a computer system is formed a set of instruction which is known as computer instruction set. Here in this example, accumulator is a register, B is a memory location, A is a memory location, T is also a memory location. First of all, by load B, we are transferring the value of B memory location to accumulator. Then by add A, we are adding the content of accumulator with A memory location and transfer it to accumulator for storing the result temporarily. Then we are transferring the result of accumulator to memory location T. So in this program there are three instructions, maybe some other program maybe more than that, more than three instructions. So total all the instructions which are supported by a computer system is basically known as computer instruction set. As I repeat earlier, a computer organization is basically a study of different components of a computer, such as arithmetic logical unit, which is responsible for performing arithmetic, logical, shifting and data transfer operation. We are able to use learn some registers such as accumulator or ACC register, which is storing the data temporarily before the operation and after the operation. and we have some and we have got control unit. What is the task of control unit? Control unit is performing the control operation, that is to say when to perform an operation, how to perform an operation, where to store the result, when to stop the operation. All these are controlled by the control unit. We have a memory unit, RAM or ROM, which will store the result, from where we can read the data, from where we can write the data. Okay, we have an input and output devices, keyboard, mouse, these are input devices, monitor, these are output devices. Okay, so we are going to use this. How input output device, how memory device, how CPU device are connected together, we need to study that. Now we need to understand that what are the benefits, what are the basically benefits of the computer instruction set. Many computer instructions are going to give us flexibility to the programmer to write more complex program, the program that they want to write. Okay, computer instructions supports number of addressing mode through which we can write many program. If all possible addressing modes are present in the architecture, it will give the lots of option for programming a particular program. However, it will be again require complex control unit. Next advantage of computer instruction set is number of general purpose registers. We require some general purpose register to write our program or to execute our instruction. What is general purpose register? General purpose registers are normally treated as B, capital B may be a general purpose register, capital C may be a general purpose register, capital H may be a general purpose register, capital L may be a general purpose register, capital D may be a general purpose register, and capital E may be a general purpose register. B stands for base register, C stands for counter or carry register, H stands for higher order address register, L stands for lower order address register, D stands for data register, E also a data register. These are mainly general purpose register. More the general purpose register, it is more easy for us to write programs. More the general purpose register, it is more easy for writing the program. System performance. The system performance can be enhanced if less number of instruction is used in the program. Okay, so if a program is executed by 3 instruction, in case of 9 instruction, then it will the system requires less number of time to compute the program. The system requires less number of space to occupy the instruction. I repeat, if a program can be written in 3 instructions without using 9 instruction, then these instruction will take less amount of time, less amount of space. So this is one of the aspects of instruction set. So we need to finalize some aspects of computer instruction set. We need to finalize some aspects of computer instruction set. Next is application. An instruction set for a particular program is designed for aiming in the certain application area. For example, a scientific computer must have a strong floating point, or scientific computer must be capable of operating complex numbers with complex number, whereas the entertainment computer must be capable of doing multimedia operation such as text related operation, audio related operation, video related operation, animation, image. These things must be there in the multimedia operation. So based on the operation, their instruction set also change. A multimedia computer must have a different types of instruction set than the scientific computer. Scientific computer needs to perform scientific operation, logarithm, exponential, factors. Okay, then we have we have to done complex arithmetic, complex addition, subtraction, multiplication, division, increment, decrement, data transfer, etc., etc. So it requires some of the instruction which supports that. So instructions is basically varies from computer to computer. An application and scientific computer application based computer requires these types of instruction, whereas a multimedia operation supported computer requires the instruction which supports text related operation, audio related operation, video related operation, animation related operation, etc. Next, our next objective is to learn instruction format. Our next objective is to learn instruction format. So as you noticed here, that instruction format, as I told earlier in the earlier class, that instruction format is basically denoted by three fields: operational code field, addressing mode field, and address field. Let me explain you with the help of an example. So this is first field, which is opcode field. Our second field name is mode field. Our third field name is address field, or operand field, or register field. So our third field name is operand field, address field, or register field. Whether I am properly audible or visible, I would like to hear it from your WhatsApp messages. Let us take an example. For example, I am talking about the instruction, say add C, A, B. Let us assume C is a register, A is a register, B is a register. which operation I want to perform? Add. To represent add instruction, I need an opcode. Let me assume the opcode is FE. So in the opcode field I should store FE. Next, I keep mode field for now empty. Currently I am leaving empty mode field. Let us first finish the operand field. Your first operand which is required for addition is stored in A register. So A register must have an address. Okay, so let me assume the address of A register is 0000. Let me assume the address of B register is suppose 0001. So these two address I must need to store in the third field, because third field will load the register address where the data is stored. Now in that register, A register, suppose data value 2 is stored, and in B register suppose data value 3 is stored. Now suppose at A register whose address is 0000, 2 data value is stored. Now B register whose address is 0001, 3 data value is stored. Now this address 0000 will be stored in a field number 3, and B register address which is 0001 which also stored in field number 3, because field number 3 either stored the data or operand directly, but here no data or operand directly specified, so this field remains empty. And or it specified the address, but C, A, B, these are not addresses, these are registers. So or it may stores the address of the register, so register address can be stored. No, I need to find it out what is the address of A register. So address of A register is 0000, so I stored 0000 to field number 3, and address of B register where my second data is stored which is used for addition 0001 which is also stored in field number 3. Okay, so now the field number, so you understand what is basically the value of field number 3. Field number 3 is 0000, which I assumed as an address of A, and 0001 which is the address of B, which is also going to be stored at field number 3. Okay, let me repeat. The one student is asking for to repeat this part without, I don't know the roll number and section of the student. I would like to advise him or her to write it down, his or her roll number and section. So I am talking about instruction format, and instruction is divided into 3 fields. An instruction format is an logical representation of an instruction. I repeat, an instruction format is a logical representation of an instruction. For example, instruction format, first field is opcode field, second field is addressing mode or mode field, third field is operand or data field or address field or register address field. So in third field either I can store the data which is used in the instruction directly, but we are observing in our instruction at C, A, B there is no data directly specified, so I cannot store any operand or data in field number 3. Next is is I can store the address of the instruction, but here is no address of the instruction is given, so I cannot store it. Or I can store the register address. Is there any register? Yes, it is. A register A is used for addition, register B is data, which is 3 is used for addition. What is the address of register A? Let me assume address of register is A is 0000, so I stored 0000 in field 3. What is the address of register B? 0001, so I stored 0001 in field number 3, so that I can able to get informed that where the data 2 and 3 is stored. 2 is stored in A register, which is 0000, and 3 is stored in 0001 address. I think now it is clear to you. Now what will be the addressing mode? What is addressing mode? Addressing mode is an way to represent your data or operand in your instruction. If the data or operand is directly specified in your instruction, then addressing mode is direct or immediate. Sorry, not direct, immediate. If your data is directly specified or explicitly specified in your instruction, then this addressing mode is known as immediate addressing mode. If your data on which you are operating is specified by register, then it is known as register addressing mode. For example, in this example, add C, A, B. Here the value 2, which is my first data, where it is stored in A register. My second data 3, where it is stored in B register. So A register stores 2, B register stores 3, and A and B are register. So hence I should write the mode of this instruction, add C, A, B is register addressing mode. Register or reg addressing mode. So we are observing that again I am explaining. For example, in this instruction we are observing no data is specified directly in the instruction. Okay, so naturally it cannot be in immediate addressing mode. We are observing that we require data 2 and 3 for addition, but 2 is stored in A register, 3 is stored in B register. Hence we are using register for hiding or representing our operand. Hence our addressing mode is register addressing mode. Let us take another example. In this instruction, what we are doing, we are basically moving the data FF to C register. We are basically moving the data FF to C register. MV stands for move, I for immediate. MV stands for move, I for immediate. So we are immediately supplying the data FF. So FF data is explicitly defined in this instruction. FF is a data. It is an hexadecimal data. Is that data explicitly specified in the instruction, or is that data is directly specified in the instruction? Yes. Where it is moving? in the C register. So C is my destination and FF is my source data. I have represented the source data immediately or explicitly in the instruction. Hence, for MBI C, FF, the addressing mode is immediate. Hence the addressing mode is immediate. Okay, so whenever I should represent this instruction MBI C, FF, first what I need to do, I need to find it out the opcode of MBI. I need to find it out the opcode of MBI. I should write it down in the opcode field. Then in the mode field I should write immediate. In the mode field I should write immediate. And then in the third field, which is my operand field, which operand is required here? FF. Is it directly specified? Yes. So in the operand field I should write FF. So in the operand field I should write FF. Okay. So and let me take another example, say LDA. LDA 9050. LDA 9050. 9050 is basically an address where my data is stored. 9050 is an address where my data is stored. LD stands for load. LD stands for load. So we are loading the data from 9050 address. We are loading the data from 9050 address. Suppose at 9050 data value 5 is stored. Data value 5 is stored at 9050. So we are loading the data value 5 from memory location 9050 to accumulator. We are loading this data value to accumulator. So what we are doing basically, we are basically transmitting this data value to a register or accumulator register. So we are going to 9050 memory location. We are going to 9050 memory location. We are reading the data, which is 5. We are transmitting it to or loading it to accumulator, because LD stands for load, A stands for accumulator in some microprocessor or some processors. Okay, which data value is stored in 9050? Answer is 5. So what we need to do? We need to first of all write it down the opcode of LDA. First of all we need to write it down the opcode of LDA. Let me assume the opcode of LDA is 3A. Let me assume the opcode of LDA is 3A. So in the opcode field I should write 3A. And in the third field or operand field, is there any operand directly specified? 9050 is not a data, it is an address, so operand cannot be specified in field 3. Is there any address where the data is stored is specified in the instruction? Yes, 9050 is an address where the data value 5 is stored, which is directly specified in the instruction. So in the field number 3 I should write 9050. Now what is the mode or addressing mode? Addressing mode is basically we are storing the data value 5 in the memory directly. So if we go to the memory location 9050, we can directly found the data value 5. I repeat, if we go to this address 9050, we can directly found the data value 5. So addressing mode is memory direct. Memory direct. Why memory direct? Because 9050 is a memory address. If we go to that memory address, we can directly find the data 5. Hence I should write in the mode memory direct. So the addressing mode is memory direct. If you have any doubts regarding the instruction format, please tell me. Instruction format varies from instruction to instruction. Instruction format varies from instruction to instruction. Instruction format varies from instruction to instruction. Okay, for example, add C, A, B, F is the opcode, mode is register mode, addressing mode, and operand addresses are address of the A register, which is 0000, and address of the second operand, which is 3, its address is 0001. Second instruction MBIC, FF is the data, so we store the data FF in field 3. What is the addressing mode? I for immediate, so we are immediately transmitting FF to C register, so addressing mode is immediate addressing mode. It is in immediate addressing mode. And in opcode I should write the opcode of MBIC, FF. Okay, next is LDA 9050. LD means load, A for accumulator, and 9050 is the address. That means from 9050 address we are transmitting the data, which is 5, to which register? We are loading this data 5 to A register. M within third bracket 9050 means we are transmitting the content of M. M stands for memory. 9050 is a memory address, hence we are denoting it in this way. Next, what is the opcode of LDA? 3A, so we are writing 3A in the first field. What is the addressing mode? Memory direct, so memory direct we are writing in the second field. What is the memory address? Memory address where we are fetching 5, 9050, so we are writing 9050 in field number 3. So I think now it is clear to all of you. If you have any doubts, you are always allowed to ask me. Now we are concentrating on CPU organization. A design of an instruction set for a computer depends on the way in which CPU is organized. Generally, there are 3 different CPU organization with certain specific instruction. First is single accumulator organization, general register organization, third is stack organization. First is single accumulator organization. In single accumulator organization is used in early days, when we use early days to prepare the CPU. When during early days to prepare the CPU, there is only one register which is majorly used, which is known as accumulator or AC or ACC. I repeat, in early days there is only one register which we normally use, and it is known as accumulator or AC or ACC. If you have any doubts, please write it down in my official WhatsApp number. If you have any doubt, please write it down in my official WhatsApp number. Please write your section name and roll number before writing your comments. Please write your section name, roll number before writing any comments. So I am talking about single accumulator based CPU organization. In that particular CPU organization, there is only one register. Register is there. You know what is register? Register is nothing but combination of flip-flop which is capable of storing a data. Data may be 8-bit, 16-bit, 24-bit, 32-bit, etc. So instruction format in this computer uses one address field. For this, the CPU is known as one address machine and the instruction known as one address instruction. For example, if we want to perform any arithmetic multiplication, it can be defined by an arithmetic assembly level language instruction uses one address field such as multi-x. You are observing multi stands for multiplication. Multiplication between the value of the multiplication needs two data. Okay, one data is stored in accumulator or AC. Okay, because by default accumulator is going to be used and another data is stored in X memory address. As because X is a memory address, it is denoted by M within third bracket X. So X is basically the address of the operand. So suppose M of X is 3, suppose AC is 2, so 2 into 3, that is 6, so 6 will be stored in AC. After multi-X, the value or result or product is 6, which is going to be stored in accumulator register. So AC stands for accumulator register. M within third bracket X denotes the memory word or operand located at location X. So M within third bracket X denotes that X is a memory address. M within third bracket X denotes that the data which is stored at X memory address. I repeat, the data which is stored at X memory address. This types of CPU organization is first used in PDP-8 processor. Okay, and these are mostly used for process control and laboratory application. Nowadays, these types of organization is replaced completely by general purpose CPU based organization. These types of single accumulator based CPU organization has several advantages. First advantage is one of the operand is always held by the accumulator register. So this result is very short instruction. So first advantage is the instruction which is used in these types of CPU organization is very small. If the instruction is very small, it will take less time to execute and less time for fetching the opcode. But it has some disadvantage. When we need to perform the complex expression, then as because the instruction is very simple, we need to write lots of instruction. If we need to write lots of instruction, program length increase. And if the program length increase, the time to execute the program also increases. So we have evolved general register based CPU organization. In general register based CPU organization, we are observing that instead of a single accumulator register, multiple general register are used in these types of CPU organization. These types of computer uses 2 or 3 addresses. Look at that, multi is an instruction which stands for multiplication. It supports 3 addresses. One address is for R1 register, another address is for R2 register, another address is for R3 register. It supports 2 to 3 address. So multi R1, R2, R3 supports 3 addresses, whereas multi R1, R2 supports 2 addresses, one for R1 instruction register address and one for R2 register. So these instructions are known as 2 address and 3 address instruction. This instruction is known as 3 address instruction, and later one is known as 2 address instruction. Okay, each address field may specify a general register or a memory word. For example, multi R1, R2, R3, here each field specified a general register. The value of R2 register and value of R3 register will be multiplied, and result will be stored in R1 register in this example. So it meaning that the value of R2 register and R3 will be multiplied, result will be stored in R1 register. This instruction also can be written in the following way, where the designer register is same one of the source register. So multi R1, R2, so R2 contains suppose 3, R1 contains suppose 2. So what we do, we perform R1 into R2, so 2 into 3, that is 6. So we can store 6 in R1 register. So R1 is basically my source, and R1 is also my destination as well. This types of instruction is known as 2 address instruction. This types of instruction is used large number of register, result in short program with limited instruction. IBM 360, PDP-11 computers are typical example where CPU based organization can be observed. What are the advantage? Since large number of register is used in this organization, the efficiency of the CPU increases. Next, the less memory space is used to store the program, since instructions are used in more compact way. Okay, disadvantage, care should be taken to avoid unnecessary uses of register. More number of register means more computational intelligence are required. Okay, more number of registers means more memory space is required and more cost is required. So organization involve more cost, large number of register. So we need to, these are disadvantages of general purpose register based CPU organization. Next we have stack based CPU organization. Stack based CPU or computer operates instruction based on the data structure called stack. You all know what is stack. Stack is a data structure which operates in LIFO manner, last in first out. That means data to be inserted or pushed into the stack, okay, one by one, okay, from the bottom to top. Stack will increase, and whenever the pop operation will be performed, the pop will be performed top to bottom, and one by one elements from the top of the stack will be popped, and hence the stack pointer will be increased itself. Stack pointer is basically a register which holds the starting address of the topmost element of the stack. I repeat, a register that holds the address of the top operand of the stack is called the stack pointer. A portion of the memory unit used to store the operands in successive location can be considered as a stack in computers. Okay, so two operations performs in the stack which are push and pop. From one end only. Push and pop operations can performed in one end only. Okay, so push operation result in inserting one operand at the top of the stack, and it decreases the stack pointer register. Okay, so the pop operation result in deleting one operand from the top of the stack, and it increases the stack register. Example, for example, we can observe that this is basically a part of the memory that we are considering as a stack. To be a memory, a stack, all the location must be consecutive. Say this is say this is 755, say 754, 753, 752. Currently stack pointer is pointing 752 address where your topmost element 23 is stored. Okay, now if we want to push another data, say 98, then what happens? 98 will be pushed into the stack and stack pointer will point the previous address of 752, which is 751. So now currently after pushing the element 98 into the stack, our stack pointer is pointing 751. The next address 752, next address, next data 43's address is 754, next data's address is 755, next data address is suppose 756. Now if we pop 98, then what happens? Stack pointer will be incremented by 1. So during the push operation, stack pointer will be decremented by 1. Previously it is 752. After in push of 98, it becomes 751. So stack pointer address is decremented. Similarly, when pushing popping the operation, whenever we pop 98, stack pointer will point 23 because 98 is being popped and it will be popped from one end only. So 23, what is the address of 23? 752. If we pop 7 to 23 also, which is the topmost element 43, what is it address? 753. So look at that again, stack pointer is incremented by 1. That is why I have said that during the operation, during the push operation, what happens? We are basically, how to denote the push operation? Push, then memory address. Suppose we want to push it at 751. So push 751. Automatically 98 data which is stored in accumulator will be pushed into 751. Similarly, what is the format of pop instruction? Pop memory address. Suppose we want to pop it from 751. So we write pop 751. Then what happens is 98 data will be popped from the memory stack and it will be stored in the accumulator. During push operation, what happens? During push operation, stack pointer will be decremented by 1. Stack pointer will be decremented by 1. So previously you have observed that when stack pointer is pointing 23, it is pointing at 752 address. Now after inserting 98, it is decremented by 1. So 752 is the previous data of stack pointer. Now after decrementation it becomes 751. So stack pointer is now 751. Similarly, during pop operation, what happens? The stack pointer's address becomes the memory address from where we need to pop the data. So now currently, if the 98 is the topmost data, if it address is 751, so memory address from where we need to pop is 751. After popping the 98 data, what happens? Stack pointer will be incremented by 1. So now the stack pointer become 751 plus 1, that is 752. So now it is pointing 752. So this is how basically stack is work, and stack related instructions are basically useful for stack operations. One type instruction do not need an address field in stack organized computer. Okay, so this is because the operation is performed on two operands of the top of the stack. Suppose we want to perform the addition between 98 and 23, then what we should do? We should write only add. We do not need to write add stack, add top element of the stack and top element of -1 of the stack. We do not need to write that. Automatically 98 is popped. automatically 23 will be popped, automatically these two will be added, automatically result will be generated, automatically result will be stored in the top of the stack. Okay, PDP 11 HP 3000 8085 microprocessor use stack based organization. The advantage is efficient computation of complex arithmetic expressions, execution of instruction is very fast because operand data are stored in consecutive memory locations. Number 3 is, since instruction do not have any address field, length of the instruction is short, and disadvantage is program size is lengthier. Okay, as because we are only using zero address instruction here, or that is why we need more programs. Next day we shall discuss arithmetic expression evolution, subroutine, and different types of instruction such as zero address, one address, two address, three address. So I would like to advise you now to give your attendance and to give your examination. So thank you all for joining this lecture.